All right, so let's get back to our lecture on shape analysis, right? That's where we left it. Okay. And technically, we should say statistical shape analysis. All right. And remember that there is this book by Dryden and Mardia that I mentioned that you have in the library. If you want to check it out, there's actually an online version of the book that you can get through the library. So I strongly recommend that you follow the book, because I don't follow everything that I'm going to cover is not in the book, but the basic concepts are certainly in the book, right? And if you want to work in that business, it's a good book to have in your library for sure at home, because you're going to be using it at some point or another, especially when it comes to Procrustes analysis. All right, so we were talking about the planner case. So let me review very quickly the notation that we have. So we assume that m is equal to 2. Remember, that means just 2D, right? And k, it's actually larger or equal than 3, the number of landmark points, right? And then we have our variable z, which was u minus u bar. Remember, that's the mean normalized vector. And then we normalize this, right? So we divide this by the norm of that vector. And remember that this is in the complex sphere of k minus 2 dimensions, right? K minus 2. Anyone can remind me why this is k minus 2? Yeah, go ahead. Right. So subtracting the u bar, which is the mean, this is equivalent to eliminating the dimension defined by the all ones vector, right? 1, 1, 1, 1, 1, 1, 1 vector. And dividing by the norm makes all these vectors z of equal length, which means they are all on the surface of a hypersphere, right? And therefore, we are now in a hypersphere. And by definition, the hypersphere loses one dimension. So if an RK, the hypersphere is sk minus 1, right? So for, yeah, go ahead.
But does z still have the same number of components as u?
Z?
Yeah.
Well, that's a very good question. Yes. But the space that that this set of vectors are embedded into is of k minus 2 dimensions, right? So remember that you can be in 2 dimensions, right? So for example, I have x1 and x2 here for an x vector. And all my vectors might be only defined in that 1 dimension, right? And therefore, the space defined by these vectors, or where these vectors reside in, or the embedding of these vectors, is 1-dimensional, right? So it doesn't matter that I have started in R2. My vectors are really in R1, right? And in that case, it's the same. Imagine that you have 2D and S1, right? So now that in R2, the sphere that I can define as k minus 1 is S1, the circle, right? So if I say that my vectors can only be on the surface of that sphere, or that circle in this case, right? I'm going to be here. Then it doesn't matter whether I define my vectors as x1, x2. They are only on that space, right? There can never be a vector here. That's not possible. Right? Okay. This makes sense? All right. Awesome. Okay. So that's our z vector. And we can define this as all the z's such that z complex conjugate z is equal to 1 because the norm is 1, right? And z is in the complex domain of k minus 1 dimension. Okay? If you want to be precise, you'd have to say that the dimension that's lost is the one defined by all ones vector. Okay? Right? Okay. Good. Now, to remove rotation, remember that a shape is defined as all the geometric information of the object once scale, translation, and rotation has been deleted from that from it. So we still have to do that. So I'm going to define the z's as all the z's times any rotation, right? And here my rotation can go from 0 to 2 pi. Okay. And remember that I said last week that this is in fact, if you want to know that, but you don't have to know this. I'm just pointing it out for those of you that have done a good job studying the projective space, that this is in fact the complex projective space of k minus 2 dimensions. Okay, so it's the same thing. All right. So we started talking about distances. Okay, so what we want to do, remember that we are in the surface of a hypersphere. Let's assume maybe, so S1 is the easiest to draw, as I drew before. S2 would be something like this, right? It's the surface of a three-dimensional ball, right? So you can always take the ball and then just take the differential of the surface, and that's the hypersphere, right? So if I have this, and I have two sets, right? So let me draw maybe set x1 and x2. It can be something like this. This here is x1. This here is x2 that define, or maybe I should say z1, z2, to follow the notation that we have, z1, z2, right? That define the set of all my vectors that are translation, scale, and rotation invariant, right? Right? And of course, the rotation is just defined by that set, right, of all the vectors. And now I want to compute distance between these two shapes. And so following the surface of the sphere, right, I want to compute this rho here. Now, remember that I could just compute the approximation here, dp. That's just the linear approximation that I can compute, okay, the one of the distances. So the first definition that we're going to give is the full Procrustes distance. And between xi and xj, and this is going to be given, so I have, remember, xi and xj are the original vectors before they are transformed, and then I transform them to the z vectors, right? So I'm going to have the infimum of the zj minus beta cj gamma, where gamma is any rotation, so SOM, right? M, the number of dimensions, remember? And beta is just a scalar, any scalar, right? That is going to scale our shape. And now here, where z k is equal to h xk divided by h xk, right? Where H is a Hermitian matrix that we introduced in our last lecture, right? Which achieves the same thing as this notation here. Okay. One way, so if you derive these equations, I'm not going to go through all the derivations, but again, you do have them in the book. If you want to, I would suggest that you try to do them at home tonight, right, or tomorrow morning, and then you check the book. But if you follow the derivations, then the full Procrustes distance can be computed as 1 minus the sum of lambda k, all the from k 1 through m, a square, and then a square root, where Zj transpose Zi, it's equal to V lambda U, with capital lambda, it's equal a diagonal matrix of singular values, with lambda 1 larger or equal than lambda 2, larger or equal than lambda m, which must be 0 or larger. Okay. Now remember that the full Procrustes distance is nothing else than the solution that we get from linear least squares, right? We did that in our previous lecture. So you can also show that using the same solution we derived last time, that the, let's say, hat, the gamma hat for our estimate of what gamma should be, or the least squares gamma, is going to be equal to U V transpose, and beta is the sum of all our eigen singular vectors, right? So you can actually recover, right, the optimal least squares transformation between one shape and another by finding the scale and rotation, right, that best approximates them. Make sense, right? And then what's left is the actual difference between these shapes, right? So if they are the exact same shape, only up to a scale, then that distance will be 0, because I'm going to find a scalar that's going to make them equal, right? If they're up to a rotation, I'm also going to find a rotation that's going to make them equal, right? And so on. So they're always going to be equal if they define the same shape. And as the shapes diverge, and I have find the rotation and the scaling that matches them as closely as possible according to the least squares criterion, of course, then that is going to give me that distance, right? You see how this works? So the trick is you define the shape as a feature vector, right? As a vector or in a vector representation. Then you use that vector representation to measure the difference between the two, right? This Procrustes, the full Procrustes is used all the time, but Procrustes analysis, which is what we're covering now, is the most famous of all approaches in shape analysis, because it's the least square solution to shape analysis, right? So in shape analysis, least squares, it's called Procrustes analysis. What can I say? That's it. It's the same thing. So this is the least square solution. Okay. All right, so if you want to use this, the algorithm works as follows. First, compute the zi's. Then second, solve for or solve for SVD, or compute the SVD rather, should be better, the ZJ transpose ZI, right? Which is obviously the variance or covariances. And then 3, the rotation is given by UV transpose, and the scale is given by this beta, which is the sum of the lambda case, right? And now, once I have done this computation, fourth, my last step is to compute the actual distance, right? So compute the F, which is this equation right here, right? Okay. So that already gives us a way, this algorithm, this very simple algorithm, gives us a way to do object recognition, right? So with this algorithm here, you can do object recognition. Right? And we'll talk about this later in the lecture today, but this is just the most basic algorithm to do object recognition, okay? Where you use the shape of the objects, and then when you have a new object, right, you compare that object with shapes of known objects, and you see which one is closest to you, right? You had a question.
So would you set a tolerance then for the EF to say then if it's below this tolerance, then it's this shape?
We'll get to all of this much later in the course. These are implementation details of what happens when I want to actually build an actual object recognition classifier. We're not going to talk about this during shape because it's generic to all classifiers or all object recognition algorithms. But generally, it depends. The answer is it depends where your goal is. In many instances, you actually know the number of classes or categories of the object that you're going to deal with. In that case, you don't have a tolerance or a threshold. In some other instances, in many instances, you just want to do what's called the two-class classification problem, which is that object in the class of interest or it's not, period, right? In that case, the threshold that you're talking about is the threshold that determines where you're in or you're out, right? And so we'll get to all these things later on in the course. Okay, there are other definitions for the Procrustes distance. So this is the full Procrustes. Another distance is the Procrustes distance. And this is my row that I mentioned earlier, right? That I have drawn there in the board. This is the actual distance. This is the one that I actually want to compute. It's not the least squares approximation. And this, in effect, it's the smallest angle between these two sets that are on the hypersphere, right? And this is called the great circles, right? This circle, great circle, is a circle that goes around the sphere. And then the smallest one, the smallest distance in one of these great circles is what defines the Procrustes distance. It can be computed as 2 times the arc sine of dp xi xj over 2, or which is the same as the arc cosine of the sum of the lambda case that we have introduced a minute ago. Okay? So if I were to look at this geometrically, this is what I would see. If I have, so let me do this. If I have 2 points here, so what I'm going to do, as always, I'm going to take this cross-section of that circle now, actually this way. So this is the origin. So I'm going to take the cross-section through the origin so that this 2 go to the origin or the center of the hypersphere, right? And this is my whoops, okay. And this here should be my hypersphere, okay? The surface of the hypersphere. Make sense? And this is, of course, rho. This is what this measures, the Procrustes distance. And the full Procrustes distance that we have computed would be this one here with a right angle on this one. This is the full Procrustes. And then the one that we mentioned on our previous lecture, dp, right, which is right here. Now, if you want to spend more time working with this, a couple things to note. Remember that to get to these equations, you need to remember this is length. What's the length from here to that point? Anyone? What's that? What's the length from the center of the hypersphere to my point xi? Or zi, whatever, because it's on the surface of hypersphere. Now one? Where are the zi's? Hmm? In what hypersphere? One hypersphere in particular, which one? Hmm? Right, which is?
1.
Unit, right? So 1. Very good. Excellent. That's 1, right? By definition. All the points are distance 1 from the center of the hypersphere. Okay, very good. And what else? I think that's all you need to know. And then you'll see in the book that from this, you can derive, and do practice this at home because this is very useful to then derive new algorithms for yourself later on. df, this is the full Procrustes distance, is equal to the sine of rho. Actually, if you take this center line here, right, this angle is half of that angle, right? Obviously, right? I mean, duh, right? So the sine of this is actually, it will give you the full Procrustes distance, and dp, it's 2 times the sine of rho over 2, okay? All right, another way to simplify all this, which is due to mostly Kent, famous statistician, is to actually take the locally the tangent space, right? The plane, the hyperplane, tangent to the hypersphere at each of the points, each of the zi points on my hypersphere. So let's see that. By the way, if you ever do work in shape analysis or do any computer vision algorithm that does recognition or anything else based on shape, the one comparison you must provide is a comparison with Procrustes analysis, right? Because Procrustes is the simplest algorithm that you can find out there. It's a least square solution for crying out loud. It doesn't get any easier, right? If your algorithm cannot outperform and way outperform the simple least square solution, then it's probably not a very good algorithm, right? So always use that as your baseline to be true to yourself. Okay, so next one is the tangent space. Okay, so we are going to consider points on the surface of a hypersphere of k minus 2 dimensions. And we're going to find planes that are tangent to that. As I said, the most famous method or approach is Kent's, because he's the guy that popularized that. And this is called Kent's partial Procrustes tangent coordinates. And they're defined for a planar shape and are given by V equals EI theta hat, capital I k minus 1, gamma gamma complex conjugate Z, where the theta hat, it's the argument of negative gamma complex conjugate Z, which defines the actual angle between these two vectors. And V is actually in T of gamma, where T of gamma is the tangent space at the point gamma. Okay? So let's see how this works. So maybe I can draw this here. Let me do that. So I have my 2 points, let's say here and here. And now I'm going to draw the part of the hemisphere like this. Okay. And now I'll call these gamma here. Let's call this gamma. This is my Z. So if this is gamma at point Z, right, this is going to be Z times some rotation rather, right? And if I scale that, I can make this, I can move this here, right, in here by just scaling, multiplying this by a scalar, right? Not making it length 1. So I could do Z E I theta times some beta value, okay? So that's what all this means. And then the tangent space is going to be this vector, right, here, V, which is in T gamma, right? And that defines my tangent space at that point. So if I take this matrix here, right, this defines the space, right? This is all the dimensions, right, subtracted from the vector that defines my point. So the tangent space, right, of my RP or CP in the complex domain, right, that is defined by the tangent space, right, by that point. So that's this vector here that defines my plane that is tangent to that. See that? Okay. So the question then is, how are we going to, which gamma are we going to use to find that tangent space, right? I mean, one option is to find a tangent space at each point that you have, each shape, right? So if I have 1 million cars, I take the shape of 1 million cars and I find 1 million tangent spaces. That would be insane, right? What I want is a tangent space that defines a car, the shape of a car, right? So which of these 1 million points do you want to take? Well, you don't want to take any of them. You want to take some type of average, right? So we're going to use the full Procrustes mean as the point. So the full Procrustes mean shape, let's call it mu hat, can be found as the eigenvector corresponding to the largest eigenvalue of the complex sum of squares and products of our covariance matrix, right? So is the eigenvector associated to the largest eigenvalue. And of course, this is still the classical definition of a mean, right? In the least square sense that we have always used, is the eigenvector associated to the smallest eigenvalue of, let's call it S, the sum of Zi complex conjugate, right? Right? Do you use Zi or Zk? Zi, right? I1 through M. And the Zi's, as always, are pre-shapes, right? Okay, is that clear? Right? So that's the that is the full Procrustes mean shape. Super important because we'll be using this constantly, right? And this is the tangent space. All right, great. So let's get to some very basic Procrustes algorithms. So remember that Procrustes analysis is nothing else than finding a least squares match of the shape given any potential Euclidean transformation, right? So my shape transform with a similarity, right? Scale, translation, and rotation, right? Okay. And using least squares as our matching of this transformation. All right, so what happens if, let's say that we only have two configurations, okay, simplest case. Let's call them x1 and x2, okay? Now, the full Procrustes analysis corresponds to the least squares matching that we have defined before. So let's call it d square of x1, x2, right? The difference between the two, or the distance, if you prefer, which is the norm of x2 minus beta x1 times gamma minus 1k a small gamma transpose, right? And that does nothing else than find the least squares translation, rotation, and a scale that matches x1 as closely as possible to x2. Okay. Now, this distance, let's call it A. It's going to be the trace of A transpose A square root, right? Let's insert that norm. And then capital gamma is SOM, right? The special group of all the possible rotations as we introduced before. And then since this is the least square solution, we already did this last week. The least square solution to that problem is gamma hat, my solution is 0. Capital gamma hat is UV transpose. And my beta hat is the trace of x2 transpose x1 rotated with gamma, right? Divided by the trace of x1 transpose x1. Okay, excellent. Right? And as always here, I'm doing x2 transpose x1 divided by their norms is equal to the SVD U, what did I say? V gamma U transpose, right? As before. Same notation. All right. So that is the Procrustes analysis. And then there is one more, which is called the full generalized Procrustes analysis. So let's see that. And in that case, we define the similarity as, let's call it G now, G of x1. In that case, we're going to generalize it not for just x1 and x2, but for endpoints. So x1 to xn, endpoints or end shapes. 1 over n, the sum from 1 through n, all the shapes. And then what I'm going to do is I'm going to do I plus 1 to n, right? So I go through all of them. So this would probably have to be n minus 1 to be precise if you don't want to include the same ones. But since we're including the other ones, it doesn't truly matter. Beta xi capital gamma I plus 1k, right? This is the vector of all ones, as always. Small gamma I transpose, right? This is what we had before, right? Over there, that hasn't changed. Minus beta. Oh, so let me add an I here. Let me add an I to the beta because this is the scalar for the xi. And now I'm going to do beta j could be different, xj capital gamma j plus 1k gamma j transpose, right? All right. Right? Okay? Now, to minimize the least squares error, your Sx, right, that we have computed before, theoretically I should say that we have assumed that S of the mean of X is actually equal to, sorry, my bad. It's actually equal to, yeah, that's right. It's equal to 1, right? Because otherwise we'll not be minimizing the least squares error, right? Because we've assumed that the mean is the point where we take our approximation. So it has to be on the surface of the sphere, right? Okay, and any questions about this? So this is just a scalar, a rotation, and a translation that I apply to xi and xj, right? To bring them as close to each other as possible, which is the same that we did here. Here I only had to do it with 1 because I only had 1, right, or 2 points. Here, because I have every point with every other point, I have to find the correspondence, the corresponding transformations. Okay? Right? And then remember, we have seen this before. Our x bar, we can compute this as 1 over n, the sum from 1 through n of beta I xi gamma I plus 1k gamma I transpose, right? This is just the average of all my points. All right. Any questions about Procrustes? Nope. So let's see how we can use this in one of the most famous methods in computer vision for shape analysis that dates way back. That is just basically Procrustes analysis to do matching and recognition of the shape. Okay, so let's do that. And this method is called active shape models. Right. So let's get to that. Now, all the methods that we're going to cover next are trivial once you understand Procrustes analysis. And Procrustes analysis is just a minor extension of what you already know, which is least squares, right? Just least squares applied to this new domain. So it's not complicated, it's just a different type of notation that you have to get used to, right? Okay, active shape models. Famous method, still used today. Okay, so what we want to do, so Procrustes analysis allows us to do two things, right? One of the most important things that Procrustes analysis allows us to do is to compute the mean shape, right? This is already fantastic because before we started this, we had no idea what the mean shape was, right? So now we know what the Procrustes mean shape is, right? It's the least square estimate of all the shapes, right? So once I have found the least squares match between all my samples, all my shapes, right, that I have for a given object, of course. I have a million shapes of cars, right, or the shape of a million cars. Then I match them, I align them so that I translate all of them into the origin of my coordinate system. I scale them to the same size. I rotate them so that they are as aligned as they can be with regard to the least squares criterion, right? And then I compute the mean of that, right? That's the Procrustes mean. Nothing to be afraid of, just a mean. Okay. Now, once we have this, I want to understand how I need to deform that mean, to match that mean to each of the million samples of shapes of cars that I have. Because the mean shape, it's just a mean shape. It doesn't define all the possible transformations from that mean into actual cars. Because let's face it, the mean car is the shape of a car that probably has never existed, probably will never exist, right? So if I take the mean of a sedan and a pickup, I'm going to get something in between, I don't know, sedan pickup, right? That doesn't exist because you can probably not build it, and even if you build it, no one would buy it, right? So that shape doesn't exist in the real world, but what I want to know is how, or even better, what are the allowable deformations from that mean shape that will give me actual shapes that I do see in the world, right? Because that mean shape can be deformed. If I consider a uniform distribution to modify that mean shape, then every possible shape is equally likely, right? But you know that that's not true, that there are some deformations that will define true shapes of cars and other transformations that will define shapes that don't resemble a car in any possible way. So how do we find this? This is what active shape models do. All right, so let's start with our vectors. As always, let's call these xi. So I start with my xi. And my xi, it's the vector of landmark points. And let's say that you have n landmark points. So if I have n landmark points, this would be xi0, yi0, all the way to xin minus 1, yin minus 1. Right? So that's my feature vector. And let the transformation, let's call it ms theta of x, be the transformation that rotates the shape by theta degrees and scales it by a factor s. And that's applied to my vector x, right? So it will scale the shape and rotate the shape, okay? That transformation. So with this notation, we can use Procrustes analysis. So if I am to use Procrustes analysis, I can define a function e, which is xi minus m sj theta j times function of xj minus tj, right? So this is a transformation that scales and rotates my vector xj, and then I translate it, and then I want to compare this to my xi. And what do I want? I want this squared. So this is this times itself, right? So this is xi, msj, theta j, xj minus tj, right? And since we're in 2D, right, this transformation here, so let me do that here. Since we're in 2D, this transformation can be given by the similarity transformation that we have discussed like a gazillion times by now, right? Which is given by the Euler angles. So I can write here, can someone remind me, this is the what? What's that? The cosine of theta negative the sine. Oops, okay, let me leave some space. Hold on, don't copy. So the cosine of theta minus the sine of theta, and then the sine, the sine of theta, the cosine of theta, right? Now what I need, because this is going to be now, let's say I'm doing the transformation here for xj k, y, j, k, right? The two components of my j vector. So then there should be xjk minus yjk, right? And xjk plus yjk, right? So that's my transformation. And of course, then if I use that notation, then here tj, it's going to be equal to t, let's call it xj and tyj for the translation about the x coordinate and the y coordinate. How about that? Okay. And then, of course, I'm going to have to copy this as many times as dimensions I have. So I have n dimensions in my vector. So I'm going to have to copy this n times, right? So obviously, this is the Procrustes feat, right? I'm just trying to find a transformation, right? The linear least squares solution to the transformation that makes xj as close to xi as possible, right? So now, if I start with a gazillion samples or shapes of cars, right? I can align all of these shapes using that transformation, correct? Yep. See that? Now, obviously, there is a problem with this. What is the problem of using this to align all the shapes of cars or tables or whatever? What is the problem with that? Think about it. So if you want to align these landmarks, the first thing that you need to do is to do what? Detect the landmarks, right? Of course. I mean, I've never seen a picture where the landmarks are already marked, right? So that's why we spend time in low-level vision. Okay, so you use low-level vision and maybe some mid-level vision if you need to help you detect those landmarks, right? Now, are all landmarks equal or equally good? Yeah, we define 3 types of landmarks, right? Anatomical, what else? Anatomical, mathematical, and pseudo landmarks, right? Now, if you can detect anatomical landmarks, good for you. Those are the most stable, the best landmarks you can use, right? So use them. If not, mathematical landmarks are very useful. We spend a tremendous amount of time in low-level vision talking about mathematical landmarks, right? And last, pseudo landmarks. I mean, if you have no other choice, then you just have to go with pseudo landmarks, right? Which are just approximations, and you hope for the best. Well, the problem here is that all the landmark points, right? So all the xij's or k's here, xi0 and xi n-1, they're all treated equal in that metric, right? This is a metric, right? This inner product defines the distance between xi and xj, true? Right? But all of these landmark points are treated equal. But the landmark points may not be equally good, right? There may be some landmark points that you know are anatomical landmark points, and those are very stable, and you want to use them with, or you want to give higher emphasis to those points, right? Or maybe some are mathematical landmarks that are also very stable, and you want to emphasize this, right? And some pseudo landmarks that are not very stable, and you want to de-emphasize those. Now, if I want to do this, how can I modify that function E there, right? The inner product between this vector with itself to emphasize some landmarks and de-emphasize other landmarks? Well, not necessarily. I'm just looking for a way to change that metric, right? This is the square metric, right? Or the Euclidean metric, right? Which takes into account or assumes that every landmark is equally valid, right? So in other words, if I have a space where this dimension specifies the value for the first landmark, and this dimension the value for the second landmark point, the norm 2 metric is going to define a circle, right, that specifies that the distance about this axis is equally valid as the distance in that other axis, right? That this landmark has the exact same weight or importance as this other landmark, right? And that's what the circle represents, right? Now, how do we represent that in this equation? There's actually something missing from this equation that we don't have because it's not needed to make the equation correct. But if you want to be mathematically precise to define this, we're missing something in this equation. What is it? The identity matrix. Very good, right? So theoretically, you'd have to have here the identity matrix, right? So this multiplied by identity matrix by this, right? Sure, of course. In general, you can change this for any other matrix, W, right? Which, if it's a diagonal matrix, it's going to define a hyperellipsoid, right? In the space of all your landmark points. And what are you going to do? Well, if this is your, let's say that your ellipsoid is like this one here, right? Then you're saying that this landmark is much more important than this landmark, right? And if you define the ellipsoid like this, it's the opposite. This landmark much more important than this one, right? And so on. Okay? So this you can do with a diagonal matrix, right? And if you do a diagonal matrix, you're only adding weights to the relevance of each landmark, right? All right. So let's summarize this in our algorithm. So I'm going to call this the alignment algorithm. So number one, we're going to align all shapes to some other shape. You just choose one. Let's say x1, right? It really doesn't matter which one. To repeat the following. A, we compute the mean shape from the aligned shapes, right? So compute the mean shape. So now that all the shapes that I have been aligned to the first one, right? Or with the first one, I compute the mean shape. B, realign all shapes to this mean shape. And repeat this process until you converge. Okay? So repeat until convergence. And you converge, remember, when the mean shape from iteration to duration doesn't change much, right? Smaller than the threshold, right? Some epsilon. Okay, so that allows us to compute the mean shape. So now, with that simple algorithm, we have the mean shape. Now we need to find ways to define the deformations from that mean shape. Okay, so let's do that next. So given the, let's say, capital N aligned shapes, we can compute first the mean, right? The x bar, remember this is 1 over n, the sum of all the xi's, I1 through capital N, right? And we can also compute the difference between each xi and that mean, right? The variance, basically, or, well, that's still not the variance, but we're getting close. And these differentials, right, these differentials here, do allow us to compute the covariance matrix, right? Let's call it sigma x. That's not sum, that's sigma. Sigma x for covariance matrix is 1 over n, the sum of dxi, dxi transpose, 1 through n, right? Okay, now, anyone can tell me, this for a gold star, once I already have the mean and the covariance matrix, right? So this is the mean shape, and this is how every shape diverges or is different from that mean shape, right? How can I find a statistical model that will tell me how to deform that mean shape to match each of the xi samples? What is the least square solution to this that we've seen like 100,000 times? Yes. Right? Yeah. So we do an eigenvector analysis, PCA, right? So basically do an eigenvector decomposition of this. Very good. Very good. So we do, say, sigma x, capital P, P lambda, right? Where P are the eigenvectors, P2 n. Is that, and remember the pKs obviously are norm 1 because they're eigenvectors. So we have that normalizing problem. Lambda 1, lambda 2n, lambda k larger or equal than k plus 1, right? And what do these principal components, these p's, tell us? They tell us how I can modify the shape, each dimension of the shape, right, to deform my original shape, my mean shape rather, to make it into each of the xi's, right? Make sense? So if I'm in my shape space, right, so this is the shape space, right? If my mean shape is right here, and my xi's are here, right? So x1 maybe, x2, x3, x4, x5, x6, x7, right, and so on, probably the first eigenvector is going to be this one, right? That tells me if I deform that shape about this vector, right, I'm getting close to each of the xi's. That's the closest I can get, right, about this direction. And then about the second direction, I get even closer. And the third direction, I get even closer, right? And depending on which deformations I may have, one dimension is going to allow me to deform the shape in a way that adapts to specific type of cars or tables, right? And another dimension, and different type of cars, and so on, right? Excellent. So that's what this does. And then, each x is going to be equal to my mean, right? Any shape x is going to be equal to the mean plus PV, right? P, the eigenvectors, and B, the vector of coefficients that specifies how I deform the shape in each of these principal dimensions, right? These principal shapes. Okay. Now, one of the problems with active shape models is how much do you allow these coefficients to grow, right? Because theoretically, you could keep growing that coefficient, because if you go from the mean shape to a sedan, right, the mean shape of a car to a sedan, then it's going to deform to a sedan. But if you keep going, what is this going to become? I mean, right? And then remember that you still have the eigenvalues, and the eigenvalues tell you how far away you can actually go, right? Because this is the actual variance in your data. So you can use these eigenvalues to determine how far one should go. And typical values that people use, it's 2 times or maybe 3 times the square root of the eigenvalue, right? The square root is the singular variance, right, or singular value. Okay, so with that, we can now use this algorithm to find a fitting of a new shape to a model. So this is what we need to do next. Okay, actually, let me review very quickly. So let's say that we're still modeling cars, right? So I go to the internet and I download 1 million images of cars, right? Yep, so far so good. Now I use my low-level and mid-level algorithms that I already know to extract the contour of my cars, okay? And I define the shape of the car as that contour, okay? And I specify some landmarks on that contour based on some mathematical equations, so I get mathematical landmarks, right? Now, once I have this, I can define the pre-shape, right, that we have seen. And then I can align all the pre-shapes. And then once they are aligned, I can compute the eigenvectors of the covariance matrix. And that gives me the model of what a car looks like, right? A car is that mean shape that can be deformed along or about these dimensions, the principal dimensions, right? That's it. OK, now I get a new image of a car that I have never seen before. And I need to find what are the parameters in my model that best describe that new car that I have never seen. Okay? So that's our next goal, and I'll do this next time. All right? Think about it, though. All right? See you Thursday.